Number 16, we're asked to consider this solid right here. How do we describe this in spherical coordinates? So this right here gives us rho squared is less than or equal to 4, or rho is less than or equal to 2. X is less than or equal to 0. In the xy plane, that is this side over here, we can see theta is running from negative pi over 2 to pi over 2. Z is less than or equal to 0. That's corresponding to rho cosine phi is less than or equal to 0. Rho isn't going to be negative, so we can safely divide by this without changing the direction here. When is cosine phi less than or equal to 0? Exactly when phi runs from pi over 2 to pi. We aren't given any more bounds on rho, so rho is between 0 and 2. We always would have a default rho is at least 0 upper bound, at least 0 lower bound. So which one of these choices corresponds here? All of them, rho is between 0 and 2. Let's see. I'm being silly here. Why am I being silly? Because I did x was greater than or equal to 0. So cross that out. Okay, it's x is less than or equal to 0 here. We weren't matching anything. What theta values are going on here? Pi over 2 to 3 pi over 2. Okay, so that should be looking a little bit better. Yeah, pi over 2 to 3 pi over 2, so it must be d or e. And d is the one that corresponds to that one there. Okay. Select the correct integrand that fills in the blank here. So z is equal to rho cosine phi, but then we have to throw in, for the integrand, it's rho cosine phi times the standard rho squared sine phi that we throw in here. So rho cubed cosine phi sine phi, and so looks like, choice B there. No, wait, nope. I'm misreading that. Choice E is the one we want. Okay, so that's problem number 16. Problem number 17. Thin metal plate occupies a triangular region that has those vertices right there. So at 0, 0, and at 2, 1, and at 0, 3. So here is our triangular region. We're being asked to find the center of mass of the plate. We were given a density function right here. How do we find center of mass? We would have to integrate the we would have to integrate the density function over this region. That will give us the total mass. Then we'd have to integrate x times the density function, y times density function, give us moments, and then we'd have to divide moments by the mass to give us the center of mass. So let's think about how we're going to set this up. So first thing, bounds on this. We can see x is running from 0 to 2. We're going to think of this as a vertically simple region here. And then y bounds are allowed to depend on x here. So the bottom side here is going to be y is equal to x over 2. I'm going to check for yourself that y is equal to x over 2 gives us the line segment between 0, 0 and 2, 1. That's the lower bound here. For the upper bound, y is equal to 3 minus x gives us the upper bound here. Okay, so let's go ahead then and find the mass. So for the mass, we're integrating the density function on this region. So integral from 0 to 2, integral from x over 2 to 3 minus x of x plus y plus 1 dy dx. And so this is going to be integral from 0 to 2. We integrate with respect to y. So let's see here. X becomes x times y. Y becomes y squared over 2. 1 becomes y. And then we plug in y running from x over 2 to 3 minus x. Okay, so, oops, and don't forget the dx there. Okay, 0 to 2. Okay, so we plug in, it's going to be a kind of long expression coming up here. X times, we're plugging in y is equal to 3 minus x right now. X times 3 minus x plus 3 minus x squared over 2 plus 3 minus x. Okay, now we subtract off what happens when we plug in x over 2. So x times x over 2 plus x over 2 squared over 2 plus x over 2 dx. And this simplifies, this is the big mess, but this simplifies down to integral from 0 to 2, 15 halves minus 3x over 2 minus 9x squared over 8 dx. One variable integral, straightforward enough to do. You should obtain 9 here. Okay, so at this point then, so we have the mass. Now we have to calculate out two more moments here. So to find m sub y, we're integrating over the same bounds. These are the same exact bounds as we did before. And we multiply our original density, x plus y plus 1, by x. So this problem did become a little bit computationally intensive. My apologies for including it. I didn't realize when I wrote the problem on the sheet, I didn't realize how long it would end up. So I'm just going to kind of gloss over some of the details. So we would integrate this with respect to y, plug in 3 minus x and x over 2, and you would end up with 15 over 2x minus 3 x squared over 2 minus 9x cubed over 8 dx. And this gives you 13 over 2. And for the moment about the x-axis, we just need to take the density, integrate it, but when it's multiplied by y here. So this is the calculation that we would do. Once again, integrating this with respect to y, plugging in the bounds there. I'll just kind of, again, write down the intermediate step here. This integral right here. And this gives you 13 if my calculations are to be trusted. And so at the end of the day, the center of mass, how do we find the x coordinate? We divide m sub y, which is the one with the x here. So that's 13 over 2. We divide that by our total mass, which was 9. And to find the y coordinate here, we divide 13, m sub x, that's the one with x, or factor y in it, again by 9. And so this is 13 over 18, comma 13 over 9. It's a believable answer. 13 over 18 would be, 13 over 9 would be somewhere around there. It certainly looks like a believable answer to me.